So this question reads, prove that on an irregularly shaped conductor, the surface charge density is greatest at locations where the radius of curvature is the smallest. So this might be a multiple choice question where you just need to know that when the radius of curvature is smallest, it means that the surface charge density is the largest. If we were to look at that, here's our irregularly shaped conductor. We have this little part. We can say this is our radius of curvature here. Or we can have this part where we can say this perfect circle has a radius of curvature right here. Let's call this number 1 and this is number 2. So this is a conductor, and it's really important that you know this. A conductor does not have any charge on the inside. All of its charge is on the surface. So here we have our charges on the surface, but there's none on the inside. Which means that when we're calculating the change in potential, which is equal to, let's say we have some point A and we have some point B, and we're trying to calculate the change of potential between them from A to B, our equation is E dot ds, and this is equal to 0. Why? Because there's no charge on the inside. Now that also means the change of potential is 0, and this means, let's say we have potential A is the same as potential B because there is no change. It does not change. This is actually really important, so hopefully you understand that a conductor does not have charge on the inside. Now we can use this to our advantage now, because we know that to calculate the potential, we use K, Q over R. Let's calculate the potential for 1. So V1 is K, Q1 over R1, and V2 is equal to K, Q2 over R2. So as we just said, all the V's are the same, which means that K, Q1 over R1 is equal to K, Q2 over R2. We can cancel out the K, and we are left with Q1 over R1 is equal to Q2 over R2. Let's try to put everything on the same side though. So the Q is on one side, the R is on one side. We multiply this side by R2. We multiply this side by R1. We are left with Q1 R2 is equal to Q2 R1. Let's divide this side by Q2. Divide this side by R2, and then we have, I'll write it way down here. We have Q1 over Q2 is equal to R1 over R2. Now, the question is not asking us for the charge, it's asking us for the surface charge density. There's another equation now that you need to know. There's a lot of little equations here. And that is the charge is equal to the area times the surface charge density. This is supposed to be a sigma. I'm not super great at drawing them. So Q1 is going to be equal to the area of its circle. The area is 4 pi r squared, r1 squared, times sigma, which is its surface charge density, but sigma of 1. Then Q2 is equal to 4 pi r2 squared sigma 2. It's important to add your little numbers down here so you don't forget what belongs to what. We're going to retake this equation. Now that we know that Q1 is equal to 4 pi r1 squared sigma 1 divided by Q2, which is 4 pi r2 squared sigma 2, and this is equal to r1 over r2. We can cancel out our 4 pi's because those don't change, and now we are left with r1 squared sigma over r2 squared sigma 2 and 1 is equal to r1 over r2. We do not exactly like it in this form because it's not telling us much. So here on the bottom left, we can multiply our left-hand side by r2 squared. So times r2 squared times r2 squared. So on the right-hand side, now we have r1 times r2 squared over r2. And this side is going to be, the left side is equal to r1 squared sigma 1 over sigma 2. Here we have r2 on the top and bottom, so we can just get rid of the squared, get rid of here, and we can rewrite this as r1 squared sigma 1 over sigma 2 is equal to r1 r2. This side we can divide by r1 squared, divide this side by r1 squared, and our answer down here is going to be sigma 1 over sigma 2 is equal to, we're going to have r1 r2 over r1 squared. What we're going to do is get rid of this top r1, get rid of one of these r1s, and we're left with r2 over r1. So now that we got rid of all that mess, we can see that if r2 were to be bigger than r1, what that would mean for our sigma, it would mean that sigma 2 is smaller than sigma 1. And we can just look at that here. So let's say r2 is 100 and r1 is 5. So let's just look at that. 100 divided by 5 is equal to sigma 1 over sigma 2. It would mean that if we want this side to be the same as this side, that sigma 2 will be smaller than sigma 1. So if sigma 2 is also 5, then sigma 1 would have to be 100. So this is just proving that on an irregularly shaped conductor, the surface charge density is greatest at locations where the radius of curvature is the smallest.